Agents. AI agents are the hot new thing, and I believe they're here to stay. So if you want to learn how they work, you're in the right place. Typically, an agent is powered by some AI model, typically an LLM, that uses an observe, think, act loop, with tool calling to autonomously accomplish tasks. Tools in this context are functions that the agent can call. These functions execute arbitrary code. They can do anything from making web requests to the topic of today, interacting with the file system. An agent can read directories, traverse through those directories, read files, write to files, and even delete everything. You can see how this is extremely powerful and also extremely dangerous. So typically, you want to sandbox your agent, not letting them interact with the actual file system, but by some close approximation of it. An example of this is a Git work tree. The agent can do whatever it wants there and it won't mess with your project state, but it's still not a true sandbox. There's nothing stopping the agent from traversing upwards and out of the work tree. Another solution is to use a virtual file system. From the agent's perspective, it's writing files and traversing directories, but behind the scenes, those tools are manipulating some data structure that represents the file system. What data structure do we use? A very qualified candidate is SQLite, an in-memory database. SQLite is one of the most elegant systems ever built. The database tables are represented in a single file, and thus SQLite itself can be thought of as a wrapper around the file system. There's many benefits that come when using SQLite as our agent's file system. For one, SQLite is highly portable. If you want to move from one OS to another, just copy the DB file and you're good to go. Since SQLite is a transactional database, we get some nice guarantees for free, like the ability to roll back state and keep an audit log of changes. Let's look at how we'd implement a virtual file system using SQLite, with Terso's AgentsFS project as our example. Link to the GitHub project will be in the description. Our agent's file system is represented primarily by 3 SQLite tables, following a similar layout to how a traditional file system would work. The Dentry, directory entry table, stores files and directory paths. It keeps track of the names of files and directories and their relative locations. The inode table restores the file metadata like its size, just like in a real Unix system. Directories also have inode entries, but they just have their mode bits set to a directory rather than a file. Finally, the data table stores the actual file data in fixed size chunks, so a large file is split across multiple rows using the chunk index to track its position. This lets us do partial reads on files as well. We always assume there is a root inode, so to resolve a directory path, we just walk the directory tree. Starting from the root inode, we split the path, and for each segment, we look up the next inode like this. Now here's where things get interesting. Do we copy the entire host file system into our virtual file system on startup? We could, but that's very inefficient, or better than that. We use a technique called COW, copy on write. The agent can have read-only access to the host file system. When it attempts to read a file, we check if it exists in the virtual file system, and if it doesn't, we fall back to the host file system. But as soon as it wants to write to a file, we check if the file has been copied to the virtual file system, and if it hasn't, we copy that file into our SQLite backend, and thus represent it in the virtual file system. To delete files, we just pretend they are deleted by storing them in a graveyard table, usually called a whiteout table. When the agent attempts to read, we check if the file exists in the whiteout table. What we've just described is an overlay file system. You can find examples of it in Terso's AgentsFS SDK and Vercel's Just Bash. That can be your homework.